Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and today we are going to discuss a new topic named dynamic mechanical analysis of thermosetting materials under the subject of thermal analysis. So far, we have studied fundamentals of dynamic mechanical analysis, in which we studied about the instrumentations working and some of the principles related to the dynamic mechanical analysis. Moreover, we have studied some of the classical and standard examples for the characterization of inorganic materials. Today we are going to discuss more comprehensively about dynamic mechanical analysis of thermosetting materials. We have already studied that thermal analysis in thermostat characterization, that thermosetting polymers are quite unique. Unlike thermoplastic polymers, chemical reactions are involved in their use. As a result of these reactions, the materials cross-link and become set. Set, that is, they can no longer flow or dissolve. In this lecture, the behavior and characteristics of thermosetting materials would be briefly reviewed. Moreover, this lecture should be followed by a detailed description of dynamic mechanical analysis of cure processes and ending with some comments on properties of cured thermosets. Cure is illustrated schematically is shown in this figure 1 for a material with co-reactive monomers such as an epoxy diamine system. For simplicity, the reaction of a difunctional monomer with a trifunctional monomer is considered. Reaction in an early stage of cure, A to B produces large and branched molecules which subsequently reduce the size of the molecule. This figure 1 is actually the schematic two-dimensional representation of thermoset cure. For simplicity, difunctional and trifunctional co-reactants are considered. Cure starts with A stage monomers, A shown in figure A, and proceeds via simultaneous linear growth and branching to a B stage material below the gel point, as shown in figure 1b part. While the continues with the formation of a gelled but incomplete cross-linked network as in figure C, while in case of figure D, the ends with the fully cured C stage thermosets. Macroscopically, the thermosets can be characterized by an increase in its viscosity as shown in this figure 2. As the reaction proceeds B to C, the increase in molecular weight accelerates and all the chains become linked together at the gel point into a network of infinite molecular weight. The gel point coincides with the first appearance of an equilibrium modulus. This is the actually time independent equilibrium modulus and also shown in this figure too. Macroscopic, this is actually the macroscopic developmental of rheological and mechanical properties during network formation. Moreover, illustrating the approach to infinite viscosity and the first appearance of an equilibrium modulus at the gel point. Macroscopically, physical properties such as modulus build to levels characteristics of fully developed network. Beside all this figure 2 illustrates the macroscopic progresses from uncured to fully cured thermoset. The uncured thermoset, often a mixture of monomers. The mixture of monomers is a Newtonian liquid. As cure progresses, the viscosity increases with increasing molecular weight, which can be monitored by rheological measurements. As the viscosity approaches infinity at the gel point steady shear measurements reach their maximum limits. Oscillatory or dynamic rheology and dynamic mechanical measurements can further characterize material in gelation region. Note that while dynamic mechanical analysis may be applied to uncured materials or materials below their gel point. So we have to note that particularity, that is due to the dynamic mechanical analysis, it may be applied to uncured materials or the materials below their gel points. The sample will require a support such as metal shim or glass fabric or wire mesh. These are the three supports that a sample need for the DMA analysis. The first one was the metal shim, the second one should be glass fabric, and the third one should be from wire mesh. As shown in this figure, while thermosetting materials will have a dynamic modulus below the gel point, it is only above the gel point that they will have an equilibrium or time independent modulus. Dynamic mechanical analysis is specially well suited to characterized spotted samples from pre-gelation or gelled unspotted samples to the completion of cure as well as fully cured thermosets. And this figure actually shows the glass transition conversion relationship for a typical epoxy amine fitted to the equation. Also shown in the equation that relating to the glass transition and conversion. We know that the glass transition should be denoted with TG symbol. Because of the 1:1 ratio relationship between glass transition TG and conversion, dynamic mechanical analysis is capable of monitoring progress of cure reaction through measurements of glass transition as shown in this figure 4. Shown that the figure 4 shown that the glass transition time versus curves for the same epoxy system which give the same information as the conversion time curves shown in earlier discussion. To review thermo analytical techniques including diffraction scanning calorimetry DSC, rheology, dynamic mechanical analysis DMA, thermal mechanical analysis TMA, and thermogravimetric analysis TGA. DSC measures heat flow into a material which is known as endothermic process while are out of the material, and the heat which is out of the material is known as exothermic heat or exothermic reactions. Thermoset cure is exothermic. Diffraction scanning calorimetry DSC applications include measurements of glass transition, conversion alpha, the reaction rate d alpha over dt, and heat capacity Cp. These are actually the measurements which would be done successfully by using diffraction scanning calorimetric instrument. The most important is the detection of phase transition temperature or glass transition. In previous lectures, we have already studied that if a material exhibits more than one glass transitions, then the number should be start from below the melting point of that particular compound, and we should have to number the different glass transition temperatures with Roman words named as alpha, beta, and gamma subsequently if there is three glass transitions found in one material. DSC applications include measurements of TG, conversion alpha, the reaction rate, and heat capacity CP. Gelatin cannot be detected by diffraction scanning calorimetry, but vitrification can be measured modulated temperature diffraction scanning calorimetry, which is also known as MTM DSC, modulated temperature DSC. While rheology measures the complex viscosity in steady or oscillatory shear. In oscillatory shear, the advance of cure can be monitored in steady or oscillatory shear, and it can also be monitored through the gel point, and both gelation and the onset of vitrification can be detected. Dynamic mechanical analysis DMA moreover measures the complex modulus and compliance in several oscillation modes. Dynamic mechanical analysis, the subject of this discussion, actually measures the complex modulus and compliance in several oscillating modes. Gelation and vitrification can be detected, and the cure reaction can be monitored via glass transition and beyond the gel point in the absence of vitrification via modulus. Glass transition is actually beyond the gel point in the absence of vitrification via modulus. The glass transition secondary transitions below TG are glass transition, creep, and stress relaxation can also be determined. Thermomechanical analysis measures linear dimensional changes with reference to time or temperature. It is also measured sometimes under high loading. Measurements include linear coefficient of thermal expansion, which is CTE, coefficient of thermal expansion, glass transition, creep, and relaxation of stresses. Thermogravimetric analysis measures mass flow primarily in terms of weight loss, and this weight loss due to cure outgassing and thermal and thermooxidative stability. Dynamic mechanical analysis measures the complex modulus and compliance as a function of temperature, time, and frequency. Examples of sample deformation modes include fixed frequency oscillation, The fixed frequency oscillation may be single or dual cantilever, 3 point bent, it may be tension or shear sandwich. So, examples of sample deformation modes include fixed frequency oscillation, which is actually the single or dual cantilever, 3 point bend, tension, shear sandwich. It resonant frequency oscillation, creep, and stress relaxation. Thermoset properties measured include storage and loss modulus. Storage and loss compliance. Tan theta glass transition, secondary transition below glass transition, gelation and vitrification, and reaction beyond the gel points. These are the more important aspects of dynamic mechanical analysis, which would be helpful for us to measure the complex modulus and compliance as a function of temperature, time, and frequency. In terms of modulus properties measured are: number 1, storage modulus, which is E dash or G dash. Storage modulus, which is actually is a measure of stress stored in a sample as mechanical energy. Number 2, loss modulus, E double dash G double dash. The loss modulus, which is a measure of a stress dissipated as heat. Number 3 is tan theta, which is E double dash over E dash is equal to G double dash G dash, which is the phase lag between stress and strain, and a typical measures of damping or energy dissipation. So these are the some of the important aspects of dynamic mechanical analysis, which actually measures a complex modulus and compliance as a function of temperature, time, and frequency as well. This would also help us for the analysis of thermosetting materials. And so far, we have observed that there are different characterization techniques, which is actually the diffraction scanning calorimetry DSC, rheology, dynamic mechanical analysis, thermal mechanical analysis, which was known as TMA, and thermogravimetric analysis TGA. We know that DSC was quite helpful to measure heat flow into a material, and that would may be known as exothermic process, endothermic process, or out of the material, which would be the exothermic process. while thermoset is exothermic. In the case of DSE, it mostly applicable and includes the measurement of different transitions, even conversion of alpha, the reaction rate and the heat capacity. While thermomechanical analysis measures linear dimensional changes with time or temperature, sometimes under high loading. So the measurements include linear coefficient of thermal expansion, glass transition, creep and relaxation of stresses. TGA measures heat mass flow primarily in terms of weight loss. This would be the actually the description of dynamic mechanical analysis, which actually measures the complex modulus and compliance as a function of temperature, time and frequency. Thank you very much.